Thank you very much. Introduction, and thanks to the organizer of the workshop for inviting me. I will present joint work with Hrushovski and Pierre. And thanks for coming even after the cocktail. I see a little bit fewer people than usual, but maybe some will come, will join us. Okay, so here's the plan of my talk. We'll talk about, first I will say what definable equivalent retractions are, then I will prove our main result, and I will give a second proof, inequal characteristic 0, which is a little bit more explicit at the end. I think both proofs are interesting, and I want to give ideas for both. Okay, let's see. So I can take more or less Lau's talk from yesterday and just continue where he said ex-Kochen-Diershov somehow, what did he say, I don't know, shadowed ACVF. In fact, the recent maybe 15 years have shown that the model theory of ACVF is extremely rich and useful for many purposes, starting with the work of Pascal Hrushovski and Macpherson with their theory of stable domination and also classification of imaginaries, which made available tools from geometric model theory in this context, and which were then used a lot. Lau mentioned motivic integration a la Hrushovski-Kazhdan, but also, for example, the work by Hrushovski and Loeser on non-archimedean geometry, and this talk will be in that spirit. So I will add a little bit, tiny little bit on top of what they did in this talk. Okay, so this is the theory. K will always denote a model, and U a Münster model, so highly saturated elementary extension of K. Just some notation, so usual notation, valuation map is given by V, gamma K is the value group. The valuation ring OK, MK its unique maximal ideal. The residue field I denote by little k indexed capital K. And if I talk about sorts, so not mentioning the points in some particular model, then it will be O, where is it? O, little m, little k, bold, and gamma. And finally, if we talk about gamma together with the element at infinity, we call it gamma infinity, and we consider it with the order topology. So yeah, as a total order. By Robinson, as we heard yesterday, this theory has quantified domination in a natural language. For example, you can add a binary relation, x divides y if and only if the valuation of x is smaller or equal to the valuation of y. But we, contrarily to Robinson, we are interested in definable sets. So the definable sets are just the semi-algebraic ones, namely given by finite Boolean combinations of valuation conditions on polynomials. Inequalities on valuations of polynomials. What is the guiding philosophy is one tries to understand as much as possible ACVF in terms of the residue field, which is a pure algebraically closed field, in particular strongly minimal, so very, very stable, and the value group, which is a pure divisible ordered abelian group, in particular O minimal, the reduct of the closed field. Okay. So that's the guiding philosophy. It's just the same as in ex-Kochen-Diershov type results, of course. So reduce as much as possible things to little k and gamma. Okay, so here are some technical definition in general. Stable domination, I mean, since it's at the heart of the talk, I want to give at least the definition, even if I don't work with the definition. So in some theory, over some parameter set C, we let STC for stable C, the union of all stable embedded C-definable sets. And given another set B, STC of B is just a definable closure of BC inside this union of stable embedded sets. And we call a global definable type P stably dominated if for every overset of the parameters for which it is defined and any realization, whenever in this stable theory STC this independence holds, then the type of the parameter over the stable part of A is already determines the type over the whole tuple. I will give examples in a second. Just to keep in mind, for those who don't know, in an algebraically closed valued field, at least over a model, if C is a model, then the stable part is interdefinable with the residue field. So then things become very nice. In general, one has to work over more complicated sets. Okay. So an important fact, proved by Pascal Hrushovski and Macpherson, is that the definable type in ACVF is stably dominated if and only if it is orthogonal to gamma. This means that germs of definable functions to gamma are constant on such a type, and it's equivalent. Examples, the generic type of the valuation ring, so which does not lie in any proper subball. Or more generally, the generic type of the closed ball I noted with the valuation. So bigger or equal to gamma of C is the set of X such that V of X minus C is bigger or equal to gamma. This is a closed ball, and I denote its generic type by eta C gamma. And this is also stably dominated, whereas the generic type of any open ball is not. And here is by transitivity, one can, and closure under algebraic closure, one may obtain that whenever you have a tuple A over a model, say, if the transcendence degree of the field extension given by it is equal to the transcendence degree of the residue field extension, then it's very stably dominated. It's even what is called strongly stably dominated. I will not give a technical definition, but there is some isolation property you have to add. So these are very nice stably dominated types. Okay, let's illustrate what happens just in the simplest possible example. So take the generic of O. I denoted it by eta 0, 0. This 0 is for the element 0 in the field. This 0 is for the 0 in the value group. If you have a generic of O over K, and if you have a field extension, then in order to know if this A is generic over L, it is enough to know that the residue of A is algebraically independent from the residue field of little kl. So you can check things in the stable part. And to see why germs of definable functions to gamma are constant, just take a polynomial with coefficients from k and look at the value of it. It takes on a realization of the generic of O, then this is just, as we all know, the minimum of the valuations of the coefficients. In particular, it doesn't depend on A, so the germ is constant on the type. It's completely different if you take the generic of the maximal ideal, for example. Okay, good. Valuation topology. So any valued field is a topological field. You just take, it is confusing terminology-wise, take as basis of neighborhoods, you can either take open or closed balls, doesn't matter, they're both clopen in the valuation topology. And this topology is totally disconnected. Now, for any variety, you can do the same. So on affine n space, you take the product topology. On subvarieties of affine n space, you take the subspace topology, and then you glue. And in this way, you obtain a unique topology on the k points of a variety. And this is called the valuation topology, which is also totally disconnected. So not so useful for example, looking at, I don't know, fundamental groups or whatever you want to do. Topology is not so nice. Berkovich analytification is a remedy to this. It embeds V of k as a subspace, which is dense, and this space has very nice topological properties. It is locally compact, locally path connected, retracts to polyhedron, etc. I will not define it because you will see an analog of it. So this is somehow in the background, but you will not need it. Okay. Now, some years ago, Ehud and François introduced a model-theoretic analog of the Berkovich analytification, which I will explain to you now, which is a definable analog. So given a variety V over K, what is V hat? As a set, so what are the B points of this definable set? Well, it will be a definable set later. It's the set of B-definable, stably dominated types which live on V as a set. And they showed that if V is a variety definable over C, then this V hat is C pro-definable. What does it mean? It means it is given as a projective limit of C-definable sets. It's even a bit better. You can take these definable sets to be surjective, so a surjective system of definable sets. And now this is endowed with a topology, which is basically, at least it's obtained by gluing. So let's look on affine pieces. If V is affine, you take the causes topology such that for any regular f on V, the map valuation of f, which goes from V hat to gamma infinity, definable, this should be continuous in the order topology for every f. Now, why is this even defined on V hat? Well, by what we said, germs are of definable functions to gamma on constant, so I can even evaluate it on a type. That's what we do. In this case, in this way, we get this topology. If we have a definable subset, we take the subspace topology on the set of stably dominated types living on X. And in this way, exactly as in the Berkovich setting, x of k with its topology densely and with induced topology embeds into x hat of k. So why is it a subset? Well, a realized type is certainly stably dominated. There's nothing to say. So that's why x is contained in x hat, naturally. But topology, this is dense. And has the right topology. Okay. Now, notation, we need something else. So I said some types are called strongly stably dominated. It was this condition that the residue transcendence degree is the same as the full transcendence degree. The set of these is denoted by x sharp. I follow the notation from the book. Okay. This associating v hat to v is functorial. So if you have two varieties and a map of varieties between them, then you get a continuous pro-definable map f hat going from v hat to w hat. It's nice. And of course, v hat, since it's pro-definable, you can evaluate it in a model. So it's not like the Berkovich space, which is done for one field at a time, but it floats with models. So it's an object of model theory. Can look at saturated points in a saturated model, etc. Example, on the affine line, we just saw that what are the stably dominated types? Well, we either have the realized types. These are balls of radius infinity. So gamma could be infinity, then it's just the point C, which is itself stably dominated, or else generic types of closed balls. So that's why we have this equality. And they all happen to be strongly stably dominated. That's why we have this equality. This is not an accident. It holds for curves. And more generally, it holds for sets of dimensions smaller or equal to 1, and from 2 on it's false. And similarly, we can see that this can be definably given, because you just need two parameters from the field, the center of the ball and the radius, which you can give by evaluation. Yeah. Strongly was the transcendence degree of the field extension given by the tuple is the same as the transcendence degree of the residue field extension given. That is it's an Abianca extension which does not increase the where ramification no ramification happens. That is another way of phrasing it. Okay, good. No, I can phrase it differently with isolation. In general, there is a definition. I don't want to give it. There is in any theory there is you add an isolation property to the
Is there a canonical inverse system which you can associate to V in order to define V hat?
It's, I mean, it's like as canonical as categorically it could get. So whenever you,
like the algebraic universal cover.
It's given by the okay. What you do is, everything. What is behind this definability is you know the imaginaries, so you know how to encode definable types, stably dominated in definable types, and then somehow you have to give all definitions for all possible formulae, and in this way you get your projective system. If you know all definitions of the type.
But is it analogous to the construction of the algebraic universal cover in algebraic geometry?
I don't think so. I mean, no. By some analogy maybe, but I'm not at the face of it. Okay. So yeah, so it's also definable, or what they call isodefinable. It's a pro-definable set which is definable bijection with a definable one. This happens for curves also, and not for higher dimension varieties. Okay. That's for the introduction. Now let's give the main theorem of Hrushovski and Loeser. First, just some terminology. Generalized interval is just a finite concatenation of closed intervals in this gamma infinity. So it could, for example, be several copies of it. Now here's the theorem. Given a quasi-projective variety over C is a subfield of K, and given a definable, so a semi-algebraic subset of V, there is a C pro-definable continuous map from the interval across x hat to x hat. Interval gets the order topology. Interval, the initial point is II, the end point is EI, such that this rho is a strong deformation retraction onto some gamma internal sigma inside x hat. So more precisely, the following, I name it dagger hold. So at the initial point, it's the identity. All the way, it's the identity on sigma for every gamma. The final image is equal to sigma, and this final image is also the final image if you only take realized types. So you don't need to take all types, the same final image. Moreover, it restricts to a map on strongly stably dominated types. And it has this funny property that if you go to someone on the path, it has the same final image as the point itself. So that's what it says here. And more on this gamma internal bit. Sigma, this is actually not just gamma internal abstractly definably, but it's even topologically gamma internal. What does it mean? It means that it's C-definably homomorphic to a subset of gamma infinity to something. Something is not a finite set. It's a finite set, but C-definable, so there may be some, you may not be able to distinguish coordinates. So that's in order to have Galois action possible, this is necessary. Okay. Yes? The interval lives in gamma. It's a finite concatenation of closed intervals in gamma. Yeah, so that's why it is just because, if you expand to a real closed field, you don't need this, for example. Just infinity has a special role as opposed to other points in the piecewise linear world. You cannot approach infinity as you can approach 0. Because you don't have x goes to 1 over x, so you have to, yeah, okay, good. Other questions? A remark, the situation is a bit nicer if V is smooth and X is, okay, now another technical condition. So X is a Klopen definable subset of V in the valuation topology, and it's also bounded. There is a notion of bounded in an affine variety. A set is bounded if it's contained in some gamma O to the n, and in a general variety, a set is bounded if you can cover it by affine charts so that it gets a union of bounded sets locally. Okay, good. And then, if you're in this situation, it's a bit better, because then we can achieve that the interval is just 0 infinity, as we would like. I know it's confusing. The initial point is infinity, the end point is 0. There's the same problem as in Udi's talk. You have the sign confusion, valuation, or norm, and so here we pay for it, so the infinity is the initial point. Okay? And sigma embeds, so it's important, into gamma to the W and not gamma infinity U. So if the variety is smooth, you can do without this point at infinity. Okay, so this was somehow the introduction. Now I come to the topic of my talk. What happens if we have a group around? So let's first look at a general situation. We have an algebraic group G. Before I should do this, I should give an illustration. I'm sorry. I wanted to give you two pictures because else maybe too much. So let's look at projective space. So I think of projective space as a union of, I take union of two affine charts, classical charts. So it's k points, P1 of k is just a union of two copies of O. And in this way, I can represent every stably dominated type as a closed ball of radius bigger or equal to 0 in the valuation topology. So in the middle, in some sense, I then find the generic of O. And so the retraction you can do is just everybody goes inside the balls grow and grow. So outside you have maybe an element which is in P1. And along the way you have maybe eta x gamma. Gamma goes from infinity. This is eta x infinity. And this is also eta x0. And in this way, the retraction, okay, it's a tree-like thing because at some point you are starting to be the same closed ball. And so this is a nice retraction of projective space. Of course, it's trivial. But now let's look at the second example. Let's look at the elliptic curve given by this equation. So this is where we take valuation of lambda positive and characteristic different from 2. So now, this is all, again P1 hat. We look at the cover given, so this is E hat. The cover of E goes to, the tuple xy goes to the x variable. And this cover is ramified at 4 points, infinity, say 1, 0, lambda. But these two guys are closer. So if you take the minimal path, you get this picture. Now you can play the same game. You do the retraction, but you just stop when you hit this set. You stop. So you retract no longer to a point, but now you retract to this thing. Now, if you look at using Hensel's lemma, you can see that over points of these colored lines, you have fiber size 2, if and only if you're over the green part, and else you have fiber size 1. And in this way, you show that the retraction I just described lifts uniquely to 1 to this set. So Ehud retracts, like you take the retraction I described, you go until you hit this graph, and you stop, and this uniquely lifts continuously to a retraction onto this. So we see here there's a circle, and this circle will, of course, we will see it later again. Okay, good. So much for little examples in curves. Okay, now I come back to the group, sorry. Now we have an algebraic group and a definable subgroup. We can ask the question, can I do the same game, but h of k equivariantly? So h of k acts on h hat of k by translation, because if you take a stably dominated type, you translate it, it's again stably dominated. And this is, of course, a pro-definable continuous action. So we can ask, do we find the same kind of retraction as in the theorem I mentioned, h equivariantly? Well, little example, very easy one. If I do this game in P1 hat, but I only take O hat, then I retract equivariantly to the generic of O. Just here's the formula. Yeah? So gamma eta c of delta goes to eta c of minimum delta gamma, and this is clearly additively equivariant. Sorry, and the final image is a point. Okay, a little more interesting if you look at a multiplicative group. Now I first describe it on simple points, and I will draw it. Maybe I draw it first. What is the idea? What is GM? It's almost like the projective line. We have to take out infinity and 0. Okay. So this graph is called the skeleton, which we have here. So here it's open, both sides. So now what do we do in this formula? We go from 1. We do the same thing we did here, the same speed. But now if I take an element of smaller valuation, t say, I go in a slower speed as before. I go slowly. And I only go here, yeah? Okay, good. And so at time 0, I will be here. At time infinity, I started from here. The formula tells you. And then in the other chart, it's also small, but because we took 1 over x. Okay. And so this speed change makes it GM equivariant. Okay. And the final image is just the set of, well, I can realize it like on the picture. It's the set of generics of closed balls around 0. And this is definably isomorphic to gamma and also topologically isomorphic to gamma. Okay, good. Note, well, actually, if you look a bit with more abstract eyes on this example, we see that what we actually did is we took this path from 1 to the generic, which is also 1, 0 here, and we looked at it. So here it's maybe Q gamma, and then we did something funny because we then just took like what you can do convolution with your type. So if you have an arbitrary p, in order to define the retraction rho of gamma p, what we do is we take tensor product. I will explain later. It's just you take independent realizations of these two types, and then you multiply them. So you had what I explained, and this is what we do. So you take the convolution of Q gamma and p, and this is another description which is more, I don't know, with more insight of this map. Okay, good. And what we, in some sense, the rest of the talk is why can we always do this? So well, you will see in a semiabelian variety we always find such a configuration in some sense. Okay, good. Okay. What is a semiabelian variety? It's
Was K a saturated? K was a big model.
no, K doesn't have to be big. K doesn't have to be big.
So what's acting on what? HK or H? What is acting on what? Previously.
U is a saturated model, but in every model it's also true that it acts. You don't need saturation for this.
But the question, are you talking about? You're talking about what? HK? Or
It's also true for U. It's true for U as well. Sorry.
the question refers to what?
The question refers to, I want it in the definable world, so no K, no mentioning of K. I want a map rho from I cross H hat to H hat. No mentioning of the model. You have H of K acting, H acting, H. And you want that this is, sorry. H of U, for example, if you prefer, yeah, or H of U. H. Okay, good. So what is a semiabelian variety? Is an algebraic group which has a subgroup which is an algebraic torus such that the quotient is an abelian variety. It happens to be commutative and divisible. Okay. So the main theorem, what we show is that if S is any semiabelian variety defined over a subfield of a model, then we can find a C pro-definable S-equivariant strong deformation retraction rho with interval given by 0 infinity onto a gamma internal space which satisfies all these properties I had on the list, the Dagger list. So all the nice properties we had. Okay, I should say that of course, I mean there are some specialists in the audience. I mean for Berkovich analytifications of semiabelian varieties, this is super classical and follows from analytic uniformization. But maybe the point, and we can also deduce it from our theorem, by the way, without doing a complicated analytic geometry. But that's not the point of the talk. I think the point of the talk is one can do this definably. So even if we did not know that, okay, maybe then that there is another theorem in the classical world, but the whole point is tameness, like one can do this definable. Okay, good. So proof, the main result. Now I need to be a little bit, I need something from model theory. So if you have a definable group and a type, global type, I can define the translation by an element, just like this. And I say that this type is right generic if there is a small set such that all translates by elements of G of U of this type are C definable for some fixed C. And I say a group is stably dominated or strongly stably dominated if it admits a strongly stably dominated right generic type. Example, O has a generic type, which is the generic type from what I said, generic, but it was generic in the sense of, not in the sense of groups. Now it's also generic in this sense of groups. And a fact which is in the preprint by Ehud and Sylvain, if G is stably dominated, then left and right generic coincide. The generic types form a single G orbit under translation, and the stabilizer is equal to the intersection of all finite index definable groups. This is G0, but also equal to the smallest type definable subgroup of bounded index, which is G00. Okay. G is connected, called connected if G is equal to G0. Good. Now a question, is there a maximal stably dominated subgroup in a definable group? That's what we want to chase. Well, examples, like in G, the multiplicative group to the n, you can take O star to the n. This is easily seen to be stably dominated. So its generic is just the independent, the tensor product of the generics of O star. And the quotient is gamma to the n, so gamma is orthogonal to little k, so we are sure that there we didn't miss anything, so it must be maximal. But in the additive group of the field, there is no maximal one. All the gamma O's, they are definably isomorphic to O, so they are of course stably dominated, but k is just an increasing union, and there is no maximal one, because k itself is not. The valuation map shows us that, I mean, that doesn't work. Okay, good. Now a theorem of Ehud and Sylvain what can deduce from their work, actually they show it for abelian, but it easily lifts to semiabelian, is that in a semiabelian variety over an algebraically closed field, there is a maximal, so it's a strongly stably dominated connected C-definable subgroup such that n is maximal, stably dominated, and the quotient is gamma internal. Let's call it lambda. Now that's a very nice theorem. It follows from an even nicer analysis, like a very general analysis, not just for subgroups of algebraic groups, but for interpretable groups in general. If they are abelian, they know a lot, so they can show that every abelian definable group sits in a short exact sequence, where on the right-hand side you have a gamma internal group, and on the left, increasing union of stably dominated groups where the index set is large, but comes from gamma, so like here. In some sense, this is like metastability groupwise, for those who know what I mean. Okay. But here we use this term, so we will make use of this short exact sequence, so we know there is this n, which is stably dominated. You can think of O star inside the multiplicative group if you want for the rest, if you get lost, but in general, in semiabelian, this is true. And what is the proof strategy? We just want to mimic what we did in GM. So we want to first find this path, a continuous path from the zero, well, from zero now because I write it additively, from the zero of our group to the generic of the group. Where is it? Pn is the generic of the group. I want to find a continuous path along generic types of subgroups. Like in O plus, you can go from 0 to the generic of O along generics of definable subgroups in a continuous way. And then once we have this, we just do the convolution thing. So we define rho as follows. From the interval across S hat, we just take Q, so we go from gamma to Q gamma here, and then we take the tensor with the type we want to know the image of, and then we evaluate what happens. So this is what happens precisely. So gamma of rho R is the type of A gamma plus B over U, where I took a realization of the tensor product of A gamma and B. So two independent realizations over U. And okay, there's something to do. One has to show that rho is continuous. But for this, only the tensor product is a problem here. The rest is clear. It's obviously S invariant. That's not equivariant. That's not a problem. And the final image is easily computed because on simple points, it will just be the set of cosets, generics of cosets of Pn, which is parametrized by lambda. So it's gamma internal, yeah, here. And then, since this is already gamma internal, it will not increase if we plug in stably dominated types. So if we plug in S hat of U, because we have this equation. If you have a gamma internal set, then the only stably dominated types on it are the realized ones. Okay, so that's the strategy. Do exactly the same as here, but now the picture is maybe different because in the end it might not be constructible. So the idea is, so maybe this is a set of code. So Pn, this is maybe Pn, and this is maybe Pn plus something. And this is parameterized, this is definably isomorphic to lambda, which is gamma internal, this thing here. And somehow we try to go in like we did from 1, and we just do it equivariantly on the whole circle. Okay. So that's the proof strategy. So if we can implement this, then we get the following a little bit amended result. Everything is the same, except that at the end we know that the skeleton is indefinable bijection with lambda canonically, because I do it this way. The same theorem as I already stated. There is an S-equivariant pro-definable strong deformation retraction of S hat to a gamma internal thing, but the gamma internal thing is now just S mod n. Yes?
If S was actually a Abelian variety, do you get a simpler statement?
No. No, it's the same. Nothing simpler. No. Okay, now I didn't define tensor product. Now I should do it. But tensor product is just, if you have two global types, you first realize Q, and then realize P generically over the realization. I should say that if it's stably dominated, it computes. In general, it will not commute. But assuming that both are C-definable or stably dominated or strongly stably dominated, the tensor product will be as well. Now we have this map tensor from V hat times W hat to V times W hat. This is certainly pro-definable, that's easy to see, but it is in general not continuous. There's a simple example. You take the diagonal, so you take V equal to W equal to A1, the diagonal inside A2. Its hat space is closed by the division of the topology, but the preimage under tensor is just the simple points of the diagonal here, because in order to, I had to realize them generically, so I cannot be equal in the image unless I was already realized in the beginning. So that is the drawback. Okay, but, and this is what we need, there is some continuity. So namely, if you take varieties and you take a definable gamma internal subset of V sharp, so strongly stably dominated types, then if you restrict tensor to that side, on one side you can keep the full W hat on the other. This map is continuous. So that's the only bit we need, because in this map we had only a gamma internal. We only, on one side, we only had the image of this path, group path, and so it's okay. We only need continuity there. Okay, that's a technical result. I think one can prove it directly. I saw in your Wolfach lecture, François, but in the book it's not. I mean, we deduce it from the main theorem, which is a little bit odd, because it should be true without using the main theorem. And I think I should go through that to understand why it's true. Okay, good. So now I give the first proof, the finish of the first proof. So suppose N is connected, strongly stably dominated subgroup of an algebraic group G, such that it has full dimension, which is certainly the case for the group found by Sylvain and Udi. It's easy to see that, because it's a subgroup, that such a subgroup is clopen in the valuation topology, and one needs to show something, it's also bounded. This comes from stable domination, but it can be shown using the Chevalier decomposition. Do it for the linear part and the abelian variety part separately. Okay. I should say maybe for those who know, this means that the hat space of N is definably compact. But I won't use it. I just tell you. Dim is a dimension in the sense of ACVF. So it's a dimension of the Zariski closure. This means that the Zariski closure of N is equal to G, if G is connected, which I can assume from start. Okay, so N hat is definably connected because on general grounds it has finitely many connected components, and N acts definably on it, but N is connected, so the stabilizer, and it acts transitively. So the stabilizer must be everything. So the orbit is only one element. Okay. Follows from the main theorem I just said that there is some path. There is some path here going from, oh, actually it's not true. A little bit more complicated. I should make another picture. Sorry. There is, the skeleton was inside, I said, because it's smooth and clopen, so we have the condition. So I can go from 0 here to the skeleton, but here maybe my Pn is somewhere, I don't know, and I also have to go here. But this path is finite. This path is finite. It's connected gamma internal, so I can really draw a path here. And this, here's a bit of infinity, but it's only once. So this path, I can draw it. Okay. So in that sense, I can go from 0. I find some path which, by the properties of the fact that N hat is stabilized under the retraction, is fully lying in a hat. Okay, so I find this path, very nice. But now, from now on, we assume that it's commutative, this group. For the next constructions, we need it, because now we take alternating sums. So for a starting Morley sequence, so sequence of independent realizations of S, I take S plus minus N to be the type of C where C is just the alternating sum of the AIs and BIs. And Hrushovski have shown, it's some version of Silber indecomposability if you want, but some elusive version, that for D, if I do this alternating, after these steps, I must have the generic of a group. And it's even the generic of a strongly stably dominated definable group. So you do this, but then you somehow average. You average this to get a nice path, which is like here. Okay. Okay, so we're done. Because we know that tensor product, here is also tensor product involved, but this was continuous. Everything is gamma internal and lies in the headspace. So we found this continuous path and we were done. First proof. Okay. Now the second proof is completely different. It doesn't use the retraction theorem by Hrushovski and Loeser. It only uses continuity of tensor product apart from more basic machinery. Okay. So an explicit one in equicharacteristic 0. It also gives something which one can still do for non-commutative groups. So that's why it's maybe also interesting. So now some digression, maybe for Anand. Take a complete NIP theory eliminating imaginaries and take some parameters. Take a stable embedded C-definable set, D, and call int C of D the union of all stable embedded D internal C-definable sets. Okay. Now one can prove that whenever you have a C pro-definable stable dominated connected group, it has a maximal D internal quotient. So there is a homomorphism, little g from capital G to this funny GD, such that funny GD is internal D internal, and is maximal such in the sense that every other such morphism has to factor through this. Okay. Moreover, we know that the generic type of, so if you take a generic of G, the generic of the image, homomorphic image, is the full definable closure of the generic, so you don't lose any information. The generic of GD is interdefinable with a long tuple here, definable closure of CA intersected with this internal closure. So everything is possibly could live as a group, there will live as a group. Okay. So one proves it like it's in stable theories. We all know this theorem, and it's a little bit more complicated. Actually, it is true for generically stable because one only needs strong germs to prove this. So by a result of Adler-Casanova's Pillay, for generically stable types, one has strong germs. So proof holds in a greater generality. Okay, we will use this now to get a canonical scale. So first, we will use it for the following D. D will be quotient of O by a definable subgroup. This definable subgroup could be gamma M or gamma O. By a result of Hrushovski-Tatarsky, these guys are stably embedded in ACVF. So we can use the abstract construction there. Okay, here's a scale lemma. It's just a name, but so we work now in characteristic 0, 0. And there is an intrinsic understanding of a subgroup I of O, because we know that if you have two such, J is contained in I if and only if O mod I is O mod J internal, or almost O mod J internal, where you replace definable by algebraic closure. So somehow it's an intrinsic scale. And it follows that O mod I to the D is the maximal O mod I internal quotient of A to O to the D. You may wonder why this is not very interesting, maybe. But actually, it will turn out to be interesting because if you use this, so you have O to the D, we have I to the D maybe, let's call it gamma O to the D, and then we have smaller group gamma M to the D, and so on, yeah, maybe delta O to the D, and then delta M to the D. Nice scale. What is the quotient here? The quotient is isomorphic to little k plus to the D. What we will do, find exactly the same thing on the n side. It's like a linearization. So we will find, here's n. We will find groups n gamma plus, which replaces the maximal ideal, such that the quotient is isomorphic to a d-dimensional k algebraic group for every gamma, and they lie nicely in each other. So how do we do this? It is told us by the scale lemma tells us that it makes sense then. Let's see how we do it. First, I should say this fails in positive residual characteristic. That's why we need characteristic 0, 0 for this. Yeah, okay. First one corollary. We will come to this in a second. Sorry, one corollary. We don't want to apply it only to generics of O to the D, but if you have an arbitrary strongly stably dominated types, at least in its definable closure, there is a generic of O to the D, by definition almost. And so we find such a guy, such that over C4, whenever I want to understand the internal closure in O mod I can do it using these quotients because I have little 2. Up to interalgebraicity, because by the theorem I know that the generic is given by the image of the generic. That's why I know that all these guys are enough to generate the definable closure with O mod I to the D. I know this. So I can transport somehow from a generic of O to the D to an arbitrary strongest stable denominated type this information up to algebraicity. We will use it now to transport the linear situation. You can think of the tangent space. It's not true, but you can think of it. Then we go here. But because we don't do it only in the little, we go until the size of n with this. So now back linearization. So let G be an algebraic group. And n strongly stably dominated, connected C-definable subgroup. Not necessarily commutative for this. No. Well, for any gamma, we just do what we did for gamma O. So n gamma is the kernel of this homomorphism I described to the maximal O mod gamma O internal quotient. The kernel of it. If I do this on the linear side, I get exactly what I want. But I do it here now. And it gives me a recipe to get a scale. Okay. Same thing, n gamma plus, but with gamma m instead of gamma O. So the kernel of the maximal O mod gamma m internal quotient of n. Okay, can do it. And here's the lemma. They are all definable. The quotient for every gamma is of the right Morley rank. In particular, it shows that this guy is stably dominated because the generic of this type lifts to necessarily a generic. And it's also nicely continuous. So if you take the union of proper closed subballs, you obtain the maximal ideal, and the same thing happens here. Exactly the same. Nice continuous. Okay. Now a theorem, what we show is that actually doing this, it's also continuous, and it gives us another way to construct this path. Now we're done. Second proof. Okay. But just using somehow transporting with this idea of internal quotients, this scale to the side, to the semiabelian side, or rather to the, it's now even an abstract, whatever it comes from, stably dominated group. Now to finish, I want to give an application, relationship between the quotient S mod S00 and homotopy type of Berkovich space. So now at first, let S be semiabelian with n maximal stably dominated subgroup and lambda the quotient I said. Since n is equal to n00, I said it because it's connected, the quotients are the same if I compute it on the lambda side or on the S side. It means the complications coming from the G00 construction entirely lie in the O minimal world, as do the topological complications. Good. And working in an expansion to a real closed field, we can then show, because it's an abelian group, definably compact, it must be a real a torus over this real closed field of the right dimension, lambda itself. And so the quotient by lambda 00 must be the real torus of dimension n. So now we can think of Pilec's conjecture and its solutions. But first, in the definable category, we know that the definable homotopy type of S hat, again with gamma expanded to a real closed field, is completely encoded in this S mod S00 with the logic topology. And even better, in the Berkovich world, they are homotopic. So if you have the same situation over a complete algebraically closed valued field with Archimedean value group, so you can construct the Berkovich identification, and then you can show, using this result, descending it to the Berkovich world, that S mod S00 endowed with the logic topology, so closed sets are preimages of tight dimensional sets in S. Sorry, the other way around. That they are homotopy equivalent. Good. Now to finish, just a little variant on our main theorem is this corollary. So if you have a subgroup of an algebraic group which is connected, strongly stably dominated, then the proof shows, of course, I just did it, if we don't perform the construction on the whole, but just on n hat here, then of course you retract it to the generic of n. That is what is explained in this corollary. So in in any situation, also in non-commutative situations. And the question is, does this also hold for non-commutative n in any characteristic? And I think that the work of Halevi on stably dominated subgroups of algebraic groups should or could very plausibly give a positive solution to this as well. Okay, thank you.